Welcome to Business Analytics. This is Hari Rajgopalan, and I'll be your instructor for this lecture. So we're still in descriptive analytics, and in reality, what we are talking about today kind of is now getting to the point of predictive analytics. So this is kind of an overlap between descriptive and predictive analytics. We are going to talk about hypothesis testing. And hypothesis testing is a big part of statistics, which of course, which is a big part of descriptive analytics. And we'll talk about what this is, but we'll first talk about why we should perform statistical hypothesis testing. And this is a form of inferential statistics that allows us to draw conclusions about an entire population based on a representative sample. Now remember, the sampling has to be done correctly, properly, and of course, getting a sample is cheaper, more practical, and easier to do than kind of observing an entire population. So for making things convenient, we have to pay a price. There's a cost to this. The cost is there's going to be an error. Sample statistics, as we know, are not the same as population parameters. There is a difference between the sample statistics and the population value, and that is called sampling error or sample error. And remember, when we did the confidence interval, we did calculate this, called the margin of error. So the question then comes is the difference observed in the sample because it is actually different, or is there a sampling error? And if the sampling error causes the observed differences, then the next time someone performs the same experiment, the results might be different because the sample is different. So hypothesis testing incorporates estimates of sampling error to help you make the correct decision. So let's take an example. You're looking at the proportion of defects produced by two manufacturing methods. Any difference you observe between two sample proportions might be due to sampling error rather than true difference. If the difference does not exist at the population level, you won't obtain the benefits you expect on the sample statistics. And this can be really expensive if you make this mistake. So what is hypothesis testing? It's a statistical analysis that uses sample data to assess two mutually exclusive theories about the properties of a population. These theories are called alternate hypothesis and null hypothesis. And we'll talk more about what these mean in a couple of further slides. But really, alternate hypothesis is the theory. Normally, it's the theory you have and the reason for which you're doing this test. And null hypothesis is usually the default, or essentially that you're saying nothing is happening, there is no new phenomena, nothing has changed. And that's what null hypothesis is. So what does hypothesis testing do? Hypothesis tests assesses your sample statistics and factors in an estimate of sample error to determine which hypothesis the data supports. So when we talk about which hypothesis, we're saying alternate or null. If you use the data to reject your null hypothesis, then your results are, we call them statistically significant. Your data supports the theory that there is an effect that exists in the population level. And I'll talk about what this effect means very soon. So we're saying something's happening. If you reject your null hypothesis, you're supporting your alternate hypothesis. So what is an effect? The effect is the difference between the population value from which you're taking the sample and the null hypothesis value. So remember, null hypothesis, you're saying nothing is happening. And you're looking at this population, taking a sample, thinking something's happening. For example, there's a problem in the manufacturing process and it's creating defects. So the population from which you're taking the sample is different from your null hypothesis, which means that there is nothing there. So this difference is called the population effect. You can use hypothesis to determine if it exists and estimate the size. So null hypothesis, let's get into it. It typically states there is no effect or there is a lack of effect, often signified by H subscript O. It's usually the default theory. Nothing is happening. Everything is the same. Things are happening as they usually do. And it requires strong evidence to reject it. If you reject it, you can then favor your alternate hypothesis, which typically states that there is an effect, that there is a difference from the population from which you're actually collecting the sample and the null hypothesis distribution. So population parameter is different from the null hypothesis value. If the sample has sufficient evidence, you can reject the null and you can favor the alternate hypothesis. It's often signified by H subscript A. So let's talk about what p-values are. And you're going to use these things called p-values in your hypothesis testing. P-value is the probability that you would obtain the effect observed in your sample, or larger if the null hypothesis is correct. Tells you how strongly your sample data contradicts your null. So it's how strong your sample data contradicts your null, and lower the p-value is, it represents stronger evidence to reject the null, right? That it is less likely that the effect observed in your sample happens if the null hypothesis is correct, right? It's less likely. So it's stronger evidence to contradict the null. P-values are used in significance level to determine whether your data favors the null or alternate hypothesis. Remember again, smaller p-values give you stronger evidence against the null, right? So significance level, or alpha, it specifies how strongly the sample must contradict null hypothesis before you can reject the null for the entire population. Is defined as the probability of rejecting a null hypothesis that is true. So the probability that you say there is an effect when there is no effect. So for example, significant level of 5% or alpha of 5% means that there is a 5% risk of deciding that an effect exists when it does not exist. So let's talk about types of errors in hypothesis testing. We know because we are drawing random samples, we are not going to get 100% accuracy in hypothesis testing. And therefore, when we do hypothesis testing, you have two conclusions. So the conclusions you can draw are reject null hypothesis or fail to reject null hypothesis. And you end up with two types of errors. The two types of errors are false positives or type 1 error. That's your first error. Here you reject a null hypothesis that is true. So type 1 error equals your significance level or alpha. Remember we talked about that? So that's your type 1 error. It's same as the value. The rate at which you have a type 1 error equals that significance level or alpha. And false negatives or type 2 errors is when you fail to reject a null hypothesis when it is false. You do not usually know your type 2 error rate, but there is a high risk when you have very small sample sizes, noisy data. Noisy data has a lot of variance and random fluctuation, or small effect sizes, that there is a very close, there's not a very big distance between your null hypothesis and your population. Type 2 error also is known as beta error. So statistical power is the test correctly rejects a false null hypothesis. It is the probability that a hypothesis test correctly infers that a sample effect exists in the population. So it basically confirms the null hypothesis, and this is 1 minus beta. Power is given by 1 minus beta. So here is a good graph to look at, a table. So here's what the columns are what the test does, and the rows kind of here is the reality. So we have here test rejects null, test failed to reject null, and here in reality null is true or null is false here. So when test rejects the null and the null is true, then you have a type 1 error or false positive. When the test fails to reject the null and the null is true, that's the correct decision, and that's essentially what we should look at. When the null is false and the test rejects the null, that's the correct decision, and it means effect size exists, and this is essentially what we are talking about when we say power. When test fails to reject the null and the null is false, this is beta or type 2 error, and this is a false negative. So let's take the fire alarm analogy. Usually fire alarm is there because the hypothesis is that there is a fire, right? You have a hypothesis saying there is a fire, and then fire alarm starts ringing. Null hypothesis is the default position. There is no fire, nothing's happening. So if you have a significant level of alpha or 5%, then you're willing to accept a 5% that the fire alarm will go off when there is no fire, right? So here are two situations. There is no fire, there is a fire. And then based on the test, alarm rings or alarm is silent. If the alarm rings when there is no fire, that's a type 1 error or false positive. When there is no fire and alarm is silent, that's the correct decision. If there is a fire and alarm is silent, that's a false negative. And when there is a fire and the alarm rings, that's the correct decision. The effect exists, and the chance 1 minus this type 2 error or beta will give you this power here, right here. And now you can practice this with other hypotheses. So let's take the example of fraud detection, banking fraud detection, right? Go ahead and draw this table and talk about what the hypothesis is, talk about what the null hypothesis is, and then talk about these 4 quadrants. If you're going to do a skin test for melanoma or cancer screening, go ahead and look at that again. Jury duty. What is your hypothesis? What is your null hypothesis, right? You could practice this with other day-to-day phenomena, that there is always a type 1 and type 2 error. So practice writing them down in English so that you get into the habit of thinking in terms of type 1 and type 2 error, hypothesis and null hypothesis. So let's talk a little bit about if we were measuring, if this were normal distribution. Blue here is the null hypothesis distribution. So if a population comes from this blue figure here, bell curve here, it basically means nothing's happening. Nothing has changed, things are the same. Now this red is the alternate hypothesis. We're saying it looks like the average here has increased. Whatever this could be sales. You're saying, hey, we tried this new sales promotion and we think sales has increased. Let's take a sample, right? Take a sample and we want to see whether it has increased or not. Does it belong here or does it belong here? And normally in hypothesis tests, what we do is we take a critical value, and that critical value which we measure, right, and we say everything to the right of this critical value, we will reject the null hypothesis and say that things have changed. Everything to the left here, we will say things have not increased, and the reason there is a difference between the population value, null hypothesis distribution, and the sample values because of sampling error, right? So if I get a value which falls here to the right of the critical value, we can reject it. To the left, we fail to reject it. And here you can see this is the type 1 error, which is to the right of the critical value. So these values of null hypothesis will be wrongly rejected, whereas these values here, type 2 of the alternate hypothesis, you will fail to reject it, and that would be incorrect. So here's your type 1 and type 2 error. And what you'll see is, if you want to reduce your type 1 error, you just have to move the critical value to the right. That will reduce your type 1 error, but that will increase your type 2 error. Similarly, if you want to reduce your type 2 error, you can move this to the left, this line to the left, and take a cutoff much earlier, but that will increase the type 1 error. So there's a warning about potential misinterpretation of type 1 errors and significance level. When null hypothesis is correct for the population, the probability that a test produces false positives equals your significance level. However, when you look at a statistically significant test result, you cannot say that there is a 5% chance that it represents a false positive, right? Why? Imagine we perform 100 studies on a population where null hypothesis is true, right? That nothing's happening. We take 100 such studies. If you use a significant level of 5%, we'd expect that 5 of the studies would produce statistically significant results, and these are all false positives. But afterwards, when we go look at these significant studies, what is the probability that each one is a false positive? It's not 5%, it is 100%. They are all false positives. And that's why you want to be careful how you interpret type 1 errors and significance levels. So really the true picture of any kind of hypothesis becomes evident after repeated testing. Given the pattern of results are predominantly not significant, it's unlikely that an effect exists if we keep getting not significance. Type 2 error and power analysis. And we'll talk more about power analysis later on. Type 2 error, or beta, is the probability of a false negative. This is the inverse. The inverse of type 2 errors is the probability of correctly detecting an effect, and also called the power of a hypothesis test. This is 1 minus beta. 3 factors affect power. Sample size. More sample size will increase your power. Variability in population. So if your variance is smaller, you'll increase your power. Effect size. That is how big the effect is. The larger the effect is, the more statistical power you're going to have. Now we'll do a separate lecture on power analysis and sample size. The last we want to talk about is one error worse than the other. Is it worse having a false positive or false negative? Now each one has a cost, and it all depends on the problem and cost of making one error versus the other. Let's take an example. Let's take cancer screening. False positive means they think you have cancer when you don't have cancer. Is that worse or more expensive than saying you don't have cancer when you actually do, right? In this case, from your perspective, you would prefer them to then go take a larger sample and reduce both the errors. And that's what normally medical doctors do. They take a skin test, scratch test, and that has high false positives. So if they say something is fishy, they'll do a biopsy, which is taking a bigger sample, right? Whereas if they say you don't have cancer, there is a very, very good chance. There's a high probability you're fine, right? So in this case, they have erred at the thing of making a false positive. They're saying, let's have false positives instead of false negative. Similarly, when we come to hurricanes, right? If you come to weather effects and issues like that, You probably want to increase your false positives to say, hey, there might be a hurricane and have things under control, even though that's expensive, rather than saying nothing's going to happen and the hurricane hits you while you're in the city, right? So it's all contextual. There are other situations where it's better to have a higher false negative than a false positive. And I'll leave it up to you to think about situations like that. With this, we'll stop the first lecture on hypothesis testing. There are going to be many more lectures on this. Please look at this carefully and make sure you understand the concepts in this lecture very clearly.